That's correct.
You're sitting here. I put everything. Okay, because I guess Stephen and maybe Nico, I don't know, they left like a milk coffee, but too fast.
It's for you to. Ready?
Yeah.
Hello everyone. Very last talk of the summer school. So of course we've reserved for last the best. So we'll have Manuel Goulao telling us about quantum cryptanalysis. Floor is yours.
Hi, I hope this is working fine. Thank you so much for the presentation and to the organizers for inviting me to be here. So I'll tell you a little bit about quantum cryptanalysis. Actually, when Bill made some remark earlier on, I thought maybe it should say quantum cryptanalysis of classical cryptography. So I'll mostly show applications of quantum algorithms to break and study in general the security of classical cryptography. But I will introduce everything as we go. Good. So in the presentation, I will just give you a brief introduction to classical cryptography and cryptography in general, like background on what you will need later on. Then I will tell you what does it mean for a system to be secure against quantum attacks. And we'll study two models in particular, where we consider offline attacks or online attacks against the protocols. So to start, so cryptography is historically, I mean, you've heard this story a few times now, especially from Mina and Arthur, that it was used to communicate and send and receive messages without anyone being able to read their contents. Today, this is usually encryption, it's called encryption, but cryptography is a bit more broad than that now. I'll stick to communications for this presentation, but be aware that now there are many constructions for more elaborate things that in general, all secure communication and computation, they fall inside the concept of cryptography. So in terms of communication, I'm not going to repeat the story of the code makers versus code breakers and so on. This has been repeated a few times now. But in the middle of the 20th century, it was shown that there's this scheme. It's called the one-time pad. It's usually attributed to Shannon, but it's also, I think Arthur also referenced this, that's also said to be independently discovered, the proof, I mean, in the Soviet Union by Kotelnikov, which is also attributed to the Shannon-Nyquist sampling theorem, which I find it's interesting that they both had similar ideas by the same time in opposite sides of the curtain. Unfortunately, as I guess we also saw, the one-time pad, it only allows you to encrypt something if you have a key that is as long as your message, and once you use it, you cannot use it anymore. So it's rather inconvenient. It has other problems, like you require authentication and so on. And for all those reasons, cryptography today is mostly implemented through other schemes, namely schemes whose security depends on computational assumptions. And computational assumptions are just some problems, some instances of some computational problems that we believe they are hard to solve. I mean, we are not sure, we just believe that that's the case. One of these is RSA. I guess Nico talked a little bit about RSA. I will tell you what it is in particular. And yeah, I said I was not going to talk much about this part, but in general, cryptanalysis, like historically, people did it by hand. Then early automata, especially, well, very well known from Polish cryptanalysts, and then followed it with work in the UK. I think Arthur also talked about this for the Enigma machine of the Second World War. Then, of course, once you have computers, you can run whatever algorithms that you want in your computers to break the schemes. Of course, when you didn't have quantum computers, you use classical computers. But now an adversary is allowed to have the most powerful computer that we know, which is the quantum computer. And as I said, in this talk, I will focus on computational secure protocols. I will not talk about unconditional security, which I guess has been the main focus of the school in terms of cryptography. I think Mina also covered lots of computational cryptography, so that's fine. And of classical protocols. So I'll not go into any cryptanalysis of quantum protocols. So good. So I'll say we will stick to encryption. In computational cryptography, in encryption, we have mainly two different types of encryption. One of them is a symmetric encryption or symmetric crypto system, where two parties, they have the same key. And with this shared key, you take some plain text, you use the key to encrypt it, you transmit the encrypted document, and the other party, which has the secret key as well, is able to decrypt it. So this, for instance, one-time pad is one instance of symmetric encryption, because the same key is used to encrypt and to decrypt. In practice, we don't use one-time pad. We do use things like AES encryption. This is, again, a computational version of a symmetric encryption scheme. I also put here SHA, which is a standard. So AES is a standard for doing encryption. It's probably what you will use when you encrypt something without knowing that which algorithm you are using. You are probably using AES. SHA is used for hashing, and I'm not going into much detail into that. But the point I want to make is that in these symmetric encryption schemes, the security or the computational assumption comes from the fact that they are extremely intricate algorithms. So they do like lots of mixing, like nonlinear functions everywhere. You try to make everything as complicated as you can to try to make inverting the encryption scheme very hard without knowing the key, and very easy if you know the key, of course. So the other type is asymmetric encryption or asymmetric crypto systems in general. They are a bit different. So now they have two keys, one public key, and one private key. And to encrypt some message, use your public key. And to decrypt the message, you use the corresponding private key. And instances of these systems are the RSA, DSA for signing, the Diffie-Hellman problem, and so on. And these computational assumptions, they are based on algebraic problems with lots of structure. And this structure is what's usually used. Well, it's what gives you this nice ability to use two different keys, but it's also what's exploited when you want to develop attacks against these schemes. So today, I mean, public key cryptography is used essentially everywhere. I think Nico talked about WhatsApp messaging, but everywhere that you go in the internet, you are authenticated to the server, you are doing e-banking, and you know that you are talking to the server and you're not talking to someone that's trying to steal your money. All of this uses public key cryptography, like even using a card to pay in the store, you are using public key cryptography. So you are using this essentially everywhere. And the point is that the current schemes that we are using now, or at least until very, very recently, they are vulnerable against quantum algorithms. So there are quantum algorithms, and we'll see some that are able to break the scheme, meaning that they are able to decrypt whatever information you send. And that's especially important in the case that this information that you are trying to hide needs to be secure in the long term, because what's happening is that you can just build a massive data center. You try to hoard every information that you can that passes through your network. I mean, it's encrypted, but you can store it there. And like I'm not going to make some estimates. I know that some people did some estimates here, but once a quantum computer is available, you can just go and you decrypt everything. I mean, for whatever I bought in this e-commerce store is not so relevant in general. I mean, maybe for you it's important, and that's fair. But I guess there are many secrets that everyone can agree that should be should be safe for the long term. And those are especially important that we care about this. And this is also not something theoretical. I mean, we know that these data centers are being built in some countries, in particular in the US. I can imagine somewhere else as well. And everything is hoarded there. So this is a problem that we have today. And indeed, there's been a push to standardize new publicly cryptography algorithms, in particular for encryption and for authentication, that guarantee security against quantum cryptanalysis. Just for you to have an idea, otherwise everything is going to be very abstract. The algorithms that we used to use, so the standards would be something like RSA, and RSA is essentially, it's based on factoring in a sense, because you have, so you take some message and some public E, and you just exponentiate your message to this exponent E with some careful post-processing that you have to do. So this just by itself is not secure. And you do this operation such that you have some corresponding D, that once you take C to the D, you get back your original M. And I say this is based on factoring because all of this works modulo P times Q, where P and Q are primes. And for you to be able to compute the secret key D, you actually can do it easily if you know the factorization, because you can compute this Euler phi function, which in the case that P and Q are prime is just P minus 1 times Q minus 1. If you don't know P and Q, this is hard to compute. So, I mean, I guess we all know that quantum computers can factor, and if we don't know, or if at least we don't know how, we'll see in a little bit. But this is why if you can factor, you can solve RSA. A similar problem is discrete logarithm and El-Gamal. I'm not going to go into it, but essentially it needs to be hard that if you compute g to the x in ZQ, then it's hard to find what was the x that you started with. Good, so now we are trying to standardize, and there are actual standards now for public encryption and authentication, namely signature schemes, whose security are based on other problems that are not factoring or discrete logarithm. And these are problems that we believe we believe because no one knows an attack against these problems. They are mostly based on lattices, which are this algebraic structure. And the problem is like finding short vectors in a lattice. There's also constructions based on chains or trees of hash functions, and also on codes, so linear codes that look like random codes. And all of these schemes that have been standardized, they are based on these three problems. Unfortunately, I mean, these are very new, and I mean, the previous ones like RSA and Diffie-Hellman and so on, and El-Gamal, I mean, they are very beautiful. I mean, I was just talking with David yesterday. I mean, all of this is so simple and works so well. So the new ones, they are not like that. They are really intricate, really, in a sense, heuristic. And I mean, I think, and Arthur said the same, and it's not hard to take this position where these problems, they have not really been thoroughly studied. And that can be seen as, so two finalists to this standardization procedure that ended up with these 5 standards, I mean, they got to the final round, they were not selected. So the first one actually, I believe it was broken before the standards were announced. And essentially you can, so with just a classical algorithm, you can break the scheme in 53 hours in a laptop. And so then they selected standards, but they left some, okay, so there are also this group of other algorithms. We'll do a new round. It was called round 4 because the final round was round 3, but they have a post round. And one of these round 4 candidates was again broken. And this one was in 10 minutes in a single core. So these problems are all very new. So in a sense, I think it's fair to say that they need a deeper study. And this is only for classical attacks. So if we think of quantum attacks, I mean, this is even more important. And also we discussed a little bit during Arthur's lectures that last year there was this proposal from someone in China claiming to have an algorithm to solve some lattice problem that would, well, not target the standards in particular, but be able to solve this kind of hard problems or problems that we believe that are hard. It turned out to have a mistake. Now there appears to have some fix. I mean, this again, like code makers versus code breakers kind of thing. Yeah, I mean, it's up to your belief whether you believe on the security or not. So that's why it's also important to have this unconditional security side of things. Okay, so this is very abstract. So let's see, what do I mean about, what do I mean when I say like quantum security, right? So we are looking at computational cryptography. So the first thing that you have classical security, meaning that everyone, like the parties that participate in the protocol, but also any adversary is a classical computer or a classical algorithm. So you get something that we will call classical security. It's what you get for instance, RSA. As far as we know, I mean, maybe there's also an algorithm to factor efficiently. Again, just belief. Second possibility is that, okay, so now we allow this adversary to have a quantum computer, but everything else, like the parties that are performing the protocol, the communication, everything will be classical. So, I mean, if we do like RSA in a classical channel, an adversary that intercepts the transcript, it can run Shor's algorithm offline, and it can recover the message. So Shor is not secure against this model. These other problems, we believe that they are, and this is more or less the basis of what's called post-quantum security. Of course, ideally, what you'd really like is that everything is quantum, so the adversary is quantum, but also the parties that are participating in the protocol are also quantum, and the communication is also quantum, and this is not the same as before. And this is what we will say it's really like real quantum security. So that's our ultimate goal here. So I'll start with the first type of attacks, which are attacks that apply also in the second model, but not in the third model, which are offline attacks. So here I'm allowing the adversary to have a quantum computer, and someone is performing a crypto system, whatever it is, encryption, and the adversary is allowed to see the transcript. So if we think back to symmetric key schemes, and we think about what is the simplest thing that we can do. Well, the simplest thing that we can do is we can just run through all possible keys and try to find the correct key. And with a quantum computer, something that we can do to do this kind of unstructured search is use Grover's algorithm, Grover's search. So I'm not going into much detail into what Grover's search is. I'll give some intuition. So in a sense, you have some database with n elements, and you want to find some specific element omega. And we want to do this with fairly high probability. So what do you do? So in the classical setting, so I'm not telling you anything about the function f. So classically, all you can do is you try every possibility. And when you get your good output, then you are happy and you output omega. And this takes order of n. Should take a little bit less. Hopefully, on average, you'll after half elements, you'll find your good one. However, in a quantum computer, you can do a little bit better, and we can actually find whatever we are looking for in a square root of n tries. And to cryptography, this has the implication that, well, if I have n keys, well, now I'm assuming that my adversary can search through these n keys in square root of n times. So I should like maybe try to increase my keys to like square of the amount of keys if I want to have the same type of security that I had before against brute force attacks. So, as I said, I'm not going to go into much detail into Grover's search because, I mean, square root of n is nice, but it's not going to break anything in particular. But for you to have an intuition on how this works, and I believe many of you have seen this in some introductory course to quantum computing, but the algorithm works as follows. So you have your goal, your target solution omega, and you have the orthogonal space, and you start with some superposition of the entire domain, of the full domain, and you are going to apply these operators where you are going to first rotate along the orthogonal vector to your solution, and you start with here and you get here, and then rotate along the original vector, and then you get here, and then you repeat and you repeat and you repeat. You get more and more close to your omega solution. And then you just measure. I mean, you will fail with some probability, and then you try again, and after a while, you'll get your solution. So this O also means that you need to repeat this square root of n some constant amount of times, and you'll be fine. Okay, I mean, Grover is interesting. Like, if you want to look at the standards, so these are the 3 levels of AES security that you have in the real world. So if you have a 128-bit security, now you are down to 64 bits. We don't think this is very nice. So I would suggest that you stick with 256, AES 256. For hash functions, the situation is more or less the same. In general, the parameters are a bit nicer if you divide by 2. But the problem is, and this is just an interesting note, and I will not go into this in detail, pre-image resistance requires you to search through all elements, but you require some property that you cannot find 2 messages that map to the same output. And apparently, you can do a little bit better than Grover here, and you can actually find collisions better than square root. And actually, you can do it in cubed root by combining Grover with something that's called the birthday attack. Good. So, I mean, I forgot to say, but if you have some questions or some comments or something in particular that you want to discuss, please interrupt me.
Sorry, birthday attack?
Okay. So birthday attack is quite, sometimes called birthday paradox. It's actually a very cute thing, in my opinion, and there's a usual game that people do when they want to teach the birthday attack. I only did it once in my life and it did not work, so I'm a bit scared of doing it. But it turns out that, it goes like this. It's called birthday attack because when you have a room, so 1 year has 365 days. So you'd expect that in this room, no 2 people would share the same birthday because you'd expect that maybe you need 300 people for with a high probability for 2 people to have the same birthday. Actually, for you to have 100% certainty that 2 people have the same birthday, you need 366 people. I don't know what I'm saying until now, but you need 366 people because, maybe the first person birthday is 1st of January, 2nd of January, 3rd of January, and so on. And of course, when you get to the 366, I'm not counting, I also don't know what's the name of these years that have one more. Leap years. I'm not counting, let's say that this year is not a leap year, which I don't think it is because it's odd. So when you go to your last day, so December 31st, then the 336th or 7th, let's say, person, everything is filled, so it needs to fall in the day of someone else. But it turns out, because of this combinatorial nature, that, okay, you are checking your birthday, not just by yourself, but you are comparing it to everyone else. But everyone else is also comparing to everyone else. And it turns out that you need about 30 to 40 people for you to have like, I don't know, 3/4 probability of 2 people having the same birthday. Sorry?
23 people for 50%.
So 23 people for 50%. So yeah, so we can do it in the end just for fun, but I don't think we will learn much, so maybe we can skip ahead. But if you really want, we can try. Or I welcome you to in the bus to the airport to find out. Good. Sorry, is this okay?
It's a famous.
Yeah, it's called a.
How does it connect to practice?
Okay. How does it connect to this? So this connects to this property of collision resistance. So maybe I will erase Nico's explanation of something. Because the problem is I also didn't introduce what's a hash function. So, but that's good that we go through that. So suppose that you have some. Oh, I broke this, but I will fix it later. Suppose that you have some function that takes some input x, is very generic, and gives you some output y. And this function in particular, it has a few properties, or this let's call it hash. It has some properties, which is it should pre-image resistant. So if I give you y, it should be, also I didn't say, but so this x is arbitrary. Arbitrary domain. So, and this is fixed domain. So you see, like you can put any x that you want here. I don't know if everyone can see. Can you see? No. Yeah. You can put any x here to get some y, but y is fixed. So you have many more x's than y's. In the same sense that you have, well, if you have 400 people, you have more people than you have birthdays. And while the first thing says pre-image resistant, it means that if I give you a y, it should be hard for you to find some x such that the hash of x is y. And this is like you have to search through all x, so that we go back to plain Grover. You also require something that's called collision resistance, which is it should be hard for you to find any 2x that give the same y. So if you like twist your head a little bit, you need to find 2 people that have the same birthday. So the same paradox applies here, and actually this is classical. This is nothing to do with quantum. Yeah, was it clear? Thanks. Thanks for the question, and please feel free to interrupt. I mean, the presentation is very modular, so if we don't cover it all, it's fine anyway. Yeah.
This specifically is a classical thing. So this, and then you said that if you add birthday attack, it increases the thing, but this is just a classical.
Yeah, exactly. So like you see, like AES has parameters for 188, 192, 256, and SHA has 256, 384, and 512. So these are the double of this. And that's exactly because the security of this is already halved by the birthday attack. So this one maps to this one maps to this one, and this one maps to this one. Exactly because if you take the birthday attack to these parameters, you get this security. But with this BHT algorithm, you can actually do better. So you even reduce it more. And so for instance, SHA-256, you don't even get 128-bit security. Yeah. Bits. So this is the amount of keys of this is like 2 to the 128, which is massive, right? I mean, this is more than the number of atoms in the universe or something. It's not, but I don't know. Bill saying it's not, I don't know. I'm not a physicist. 350? 2 to the 300. Okay, fair enough. Yeah, I mean, your computer is not going to go through that. Let's say it like that. Good. Yeah. Good. There's a good point to ask questions. Okay, so I'll move on. And I'll move on to Shor's algorithm, which I'm pretty sure everyone here has heard. I'm also pretty sure many people have seen how it works. I guess some people might have not seen how it works, so I'll go through it. And I also think it's an interesting result. And I don't think we covered a lot of algorithms in the school, so I think it's nice to have. So Shor has developed this algorithm that, if you don't know, is able to factor and also to solve the discrete logarithm problems in polynomial time. And of course, this has impacts to public key cryptography, as we saw in the introduction of this talk. And these are even used today, like RSA, for instance. And Shor's algorithm, it deeply changed like the field of cryptography and of secure communications, but also the field of quantum computing. I mean, I guess you can ask to many people, and some will tell you that Shor's algorithm is probably the most useful, if not the only useful algorithm that we have that runs in a quantum computer. I'm not one of these people, but there you'll find someone that says this for sure. If you want some estimates, this is from 2021. People have, well, these people that I don't know how to pronounce the names, have estimated that you need about 20 million qubits, physical qubits, and 8 hours to break RSA 2048. So again, it's the number of bits of your key, actually of the product of the primes. Today, I mean, I don't know, 3 or 4 years after, I don't know what is the current status. I know that people try to move away from 2048 and at least double this to 4,000. Yeah, and there has been recent progress on making Shor's algorithm more efficient. And this usually goes through space-time trade-offs. And if you don't know what's a space-time trade-off, essentially you require a larger register, so larger memory, and you can reduce the time. So you can do this kind of optimization on what resource do you have better available. And of course, this led us to come to quantum-safe cryptography. Good, so I'll now explain Shor's algorithm, and please interrupt me if you need some clarification. So we will have some n, which is the product of 2 primes p and q. And we will take some a, any a, we don't care, and we define this function, which raises a, which is fixed, to the power of x, which is the input of your function, and reduces this modulo n. So I will give you just an outline, and then we go to the actual algorithm after. So you'll start by putting the full domain in superposition. You will then evaluate this function on the superposition. So essentially, this means evaluating f on every entry of your superposition. We will then do this algorithm that is the quantum Fourier transform. If you're not comfortable with this, I will also give you some intuition of what is this. And then we will measure the output, and hopefully we will recover the period of this function f. And it turns out that finding the period of the function is good enough to be able to factor n. And this is a classical reduction. This has nothing to do with quantum, and we will also see why. And so a classical algorithm to factor would require something like this. So some exponential to cube root of n times cube root of log square of n. And in a quantum computer, you can actually do it with with the cubed n. And actually, interestingly, maybe, is that the complexity comes from the implementation of the classical function in the quantum computer. It does not come from any quantum step. It comes from how you implement the classical function itself. Good. So let's start with why is it enough to get the period of the function. So suppose you have some a. So now I'm going to assume that I have the period, and I'm going to factor n. So I have some a, and I also have the period, which here I called it the order for a specific reason, but you can think of it as the period of a, which I mean that it's going to be the smallest value such that a to the r is 1. So there's no I smaller than r that gives me back 1. Of course, I to the 0 is 1. What is the next one that gives me 1? Yeah, maybe it's n. It's not n because there's no n elements, but let's ignore that. I also am going to assume for now that R is even and that A to the R over 2 is not -1. And we'll see why this is important. So, okay, first thing that we will try. We will try to do to see if A has any common factor with N. This goes through this greatest common divisor algorithm, also called the Euclidean algorithm, from more than 2,000 years ago, still very useful today. And if actually they share some factor, since we know that N is P times Q, then the factor must be P or Q. So we just return the factor and N divided by the factor, and we are done. So this is never going to happen, of course, but I mean, we should check it still. Then we will, so we do know that A to the R is 1 because of this assumption here that R is the order of A. And since A to the R is 1, mod N, of course, we are always going to be working mod N, and I'm not going to say it probably most of the times. So please know that we are always working mod N. But the fact that this is true means that N divides A to the R minus 1. That's clear to everyone? Good. However, we know that R is even, so we can actually decompose A to the R minus 1 into A to the R over 2 minus 1 times A to the R over 2 plus 1. So we know that N divides this product here. Okay. Now the critical step is that N does not divide neither this factor, neither this factor. Do you know why? Or does anyone want to guess why or figure out why? Yeah? For this one, it's an assumption, because if you put minus 1 here, it's different from 0 mod N, so N does not divide this, yeah? And for this one? Yeah? Sorry, I will try to repeat the questions, but this time I cannot repeat because I didn't even hear. Okay, good. So it would contradict that R is the order, because we assumed that R is the smallest, that R is the smallest value such that A to the R is 1 mod N, so A to the R over 2 cannot be 1 mod N. This is why I wrote this here. So if we know that N divides this product, but does not divide either of the terms individually, it means that some factor of N must divide this one, and some factor of N must divide that one. And therefore, if we check what is the common divisors of the left factor and N, and of the right factor and N, we have exactly P and Q, because N has no other factors, only has P and Q. So essentially, given the order, and the order is even, and A to the order over 2 is different from minus 1 mod N, then we can factor N. Yeah, purely classical algorithm here. Actually, I have an example here that we can go through somewhat fast. So let's take N to the 15, A7, R4. So R is even, good. 7 to R over 2 is 4, is not minus 1, good. So minus 1 is 14. So if we do the greatest common divisor of 7 squared minus 1 and 15, we get 3. 7 squared plus 1 with 15, we get 5. Of course, again, this is mod 15, because this is going to be 48. And yeah, I mean, of course, this is true. Okay. So I guess you can check. I will also put my slides available, so if you don't want to take notes, or I will give everything to everyone. So how do you do this? Okay, so please keep in mind that these conditions are not obvious. I mean, it's not going to be that for all R, it's going to be even, it's going to be true. Sometimes it's not going to be the case. And what we do when this is not the case is we are going to just pick a different A. So we are free to choose A. I'm going to do, this is not very pedagogical to go back like this, but we are free to pick the A that we want. So if this is not good for us, we just pick a new A. This feedback has been a bit recurrent through all the lectures, so I know it's not my fault. Good, so now we know how to factor given R, but we don't know R. I mean, in principle, it should be hard to find R with a classical computer. Otherwise, I could just do the previous algorithm and solve everything and solve factoring with a classical computer. So how do we do it with a quantum computer? I don't know if this is how Shor did it, and I don't think this is how it's explained in all textbooks. This is the easiest way I know how to explain it, or to be more fair, this is the most intuitive way for me to see it. Maybe it's not for you. Anyway, if you have questions, please let me know. So you take your function implemented as this quantum oracle, where it takes an input x and it writes back x, but also a to the x mod n. And you are going to start with some register of about log 2 of n squared qubits, and also a register of log 2 of n qubits. You will prepare it in the first register in the uniform superposition, and the second register you leave it alone for now. You are going to apply your function u to the preparation, giving you a superposition of x and a to the x mod n. And now just what I want to say here is that there are so t is much larger than n. So 2 to the t is much larger than n, because this is a log 2 of n squared bits, and this is log 2 of n bits. So this x is going to go around n many, many times. That means that this function is going to go around many, many times. Also, this function, a to the x, it goes around for each time that you have a period, right? The previous r. Every time that you have a to the r, it goes around once. It goes back to 1, right? A to the r is 1. But also a to the 2r is also 1. A to the 3r is also 1. A to the 4r is also 1. So this function here is going to have many cycles in it, right? And for each x, you'll have, for each a to the x, you have many possible x's that give the same result, because this is much smaller than this, right? Is this clear to everyone? So now what we are going to do is we are going to measure this second register. Just as a side note, you probably also know this, but you don't really have to measure it. We do measure it because it makes our analysis simpler, but you just can leave it alone and is exactly the same. So by measuring it, we're just going to get some a to the x0, so you'll get some random value. I mean, you don't get to choose. But the point is that whatever this value is, there's many values of x that give this result. And therefore, you'll get a superposition in the first register here of all possible values that give you y0. And why is this good? Is because all of this, so as I said, all of these values here, they give the same output when making a raised to this. And especially, they have a cycle. And every time that you go over the order, you go again back to the same place. So this is periodic. So I was just saying this, right? When you have a to the r, a to the 2r, a to the 3r, and so on, you get the same value. This is just an offset that you get because you just arbitrarily picked some value of the second register. So this function is periodic, and that will allow us to use the quantum Fourier transform. Now, probably this is the most technical thing I have. I don't think it's, I think everyone is able to follow just for what I have in the slides, but I still want to make it clear if someone does not follow and is not clear. So I guess everyone knows that this expression is 1. So if you have some x and you define some function to be this, I guess someone can, I mean, to be more pedagogical, can someone point what is the period of this function? Is 1. Because like you go, like your x goes, it goes around the circle, right? So it goes around the circle, and when x is 1, you go here, and when x is 2, you go here, and when x is 3, you go here, and so on. So what did I want to say with this? I wanted to say that what the quantum Fourier transform does is going to, so the quantum Fourier transform first is a family of algorithms for each base that you take. So in this case, we are looking at the quantum Fourier transform over 2 to the t. So it is going to do something like this. It's going to sample, it's going to do something like this. So now your period, it becomes 2 to the t, right? Because you need actually x to be a multiple of 2 to the t for this to give you 1, right? Good. So what the quantum Fourier transform does, it actually takes some state, let's say, well, I will use my own example. It takes some state, so x0 plus kr, and it is going to multiply this state by, and maybe I can put it here like that, by x to the, or I'm going to use the same variable that I used, to y over 2 to the t times whatever function you had. In our case, is x plus k and r, which was our psi 4. Okay, so that's what the Fourier transform does, the quantum Fourier transform does. Why is this useful? Well, it is useful in the particular cases that this function is periodic. And why is that? So if you ignore x0, well, maybe I will write it down so you don't have to do it in your head. So if you do e to the 2 pi I x0 or x0 times e to the 2 pi I, I'll get out of the way in a second, k r y over 2 to the t. This doesn't look an exponent anymore. Y to the 2 to the t. Again, this function here, sorry, I don't think this works. This function here is going to be periodic again, like whenever you have some y, that is going to be r over 2 to t. So here, if your y is equal to, sorry, if y is equal to 2 to the t over r, so the 2 to the t cancel with the 2 to the t, and the r cancels with r, and you get just, if you look there, 2 pi I k for some integer k, because it's the variable of the sum. So that's going to be exactly m, because it's going to be 1 plus 1 plus 1 plus 1 times m. So what this means is that this function here, or this state here, it will have peaks. So the magnitude for the values where y is a multiple of 2 to the t over r is going to be m, and it's going to be much larger than the magnitude for any other value. So if you measure this state, you will get something that is, well, we would like it to be some multiple of 2 to the t over r. And don't forget, I mean, r is the order that we want to find. And it's appearing here, so we can measure some function of it. And we have some issues, there are some precision issues. And what you do to circumvent this, and this I will skip over, but you do again a classical algorithm that's called a continued fractions algorithm, which allows you to approximate S over R. And if you know S over R, you actually it allows you to approximate S and R by just dividing this by 2 to the t. This is what is meant to be a convergent of S over R. So you can just recover R. So I have a small example here, but it's more or less the same. So you again start with n equals to 15, a equals to 7, t equals to 8. You put your x in superposition, you evaluate our function. So we know that R is equal to 4. You will measure, so the peaks will appear at these multiples. So let's suppose you measure 64. This is 64 over 2 to the t is 1/4. So R is equal to 4. Of course, I made up this example. Good. So I don't know, someone wants to ask some question here? So to recap, how does Shor's algorithm work? So you start with some random A, and as I said, you can pick this A anywhere, any way you want, and if your algorithm does not work, you will go back and pick a new A. You will check if it has common factors with N, and if it does, you are done. Otherwise, you find the order of A, and you need to do this classical processing to approximate whatever comes out of the quantum algorithm. You check if R is the order of the order of A, and this I forgot to say, this is not very important, but there's an issue. So let's suppose that S is equal to 2. So in this case, I cheated and I put S equal to 1. But if S is equal to 2, S will have a common factor with R. And if S has a common factor with R, this does not work. You will recover 1/2. And 2 is not the order. So we will reject. So this can happen if the order and the multiple have common factors. If they do, you just try again. If R is not even, you need to try again. And if A to the R over 2 is not, is different, sorry, is equal to -1, you need to reset. Otherwise, you are done. So what I didn't tell you, and I'm not going to tell you, is that it's possible that this random sampling gives you a good A. This is not obvious. I guess from all of these, this is not the less obvious one. And maybe the last one is. I also didn't tell you how to compute the GCD and the continued fractions algorithms. You just have to believe me and check some textbook. I mean, this is standard, classical, and efficient. I didn't tell you how to implement U. This you can check in Nielsen Chuang. And I also didn't prove anything related to the fact that these peaks on the magnitude of the good elements of Y, they are sufficiently separated and sufficiently sharp that when you measure your state, you get to a good Y. I also didn't show you this. This is also not obvious at all. I guess this is the homework of this presentation. Yeah, I mean, I guess this is the most technical thing that I will cover. So if someone has some question, it's good. Good. So I'll just briefly go over this because this is more like state of the art kind of thing. So it turns out that Shor's algorithm is a specific instance of a more general family of problems that are called the hidden subgroup problem. And the hidden subgroup problem, it asks you to find some periodic, I mean, again, this keeps coming because it's the same family of algorithms, that if you have some group G and some function that maps G to some other set, and you have that this function is constant on the cosets of some unknown subgroup H of G, the problem asks you to determine the subgroup H. This is why it's called hidden subgroup. Just to give names to these things, so suppose that you have the integers from 0 to 7, and you have some function where you reduce mod 4, then, of course, 0 and 4 give 0, 1 and 5 give 1, 2 and 6 give 2, 3 and 7 give 3. And this is what's called a coset because, well, you can imagine that this is an offset of 1 of this is one offset of 2 of this is one offset of 3 of this. And the hidden subgroup problem asks you to find H, so to find 4. So I guess, of course, this 4 is the thing that we found with the quantum's algorithm. How is it connected to Shor? Well, the group, I mean, if you don't follow what is a group, what is a coset, I mean, you can just ignore this slide. It's just mostly conceptual anyway. Your group is going to be the integers up to n squared. This is where we took the t to be 2 to the t, so the t is log 2 of n squared. The function is modular exponentiation, and the hidden subgroup is again, well, 4 is the multiples of the order of A. Good. I don't want to waste too much time on this slide. But to give an overview, so now there's many problems that fit inside of the hidden subgroup problem. We have Deutsch's problem, Simon's problem, so on. We have Shor's algorithm for both discrete logarithm and factoring. And we also have these very interesting two ones over here, which have algorithms, but the algorithms are not efficient. And apparently that's because these problems, the groups themselves, are not abelian. And this last one is especially interesting because if you remember the introduction to the talk, this is the basis of the new lattice-based cryptography assumptions. So this is an instance of the hidden subgroup problem. It's just it's not abelian. We don't know an algorithm to solve it. So now I don't have too much time. I think I have 15 minutes. So I will go over this second part a bit faster. So now, I mean, all that we covered, we checked, oh, what happens if I have a quantum computer offline? But now we are going to ask, oh, what if we can actually interact with the systems with quantum inputs, with quantum states? So this I more or less covered. So if you want to compute some classical function in a quantum computer, you need to encode it somehow. And you have some constraints when you encode it. And the main constraint is that your computation needs to be unitary. It needs to be reversible. So the trivial encoding that you have, and the one we will use, is that if you take some function, some classical function that takes an input x and returns some output y, you can just replicate your input x as the output and output the f of x, the y. Why? Because then, if you know the input, you can compute the function f and subtract f of x from here, and it goes back. So this is what I have here. So for instance, if you want to compute the AND, which is A and B, you just keep the AND A plus B, and you can uncompute this from here because you know the inputs. If you don't know the inputs, it's not possible to go back. Actually, this is clearly not injective because it's 2 bits and this is only 1 bit. So this is more or less how you encode this unitaries U. You take some cat X as the input and some output register Y that I represent here, and you just write your output of your function here in the output register, as we said. And the interesting thing is that now you can actually put X in superposition, and this will have a significant impact on what will happen here. And that's what you will use to analyze security in this setting. This is one trick. I will tell you because it's nice. I'm not going to use it because there's no time. If you actually put the output register Y as the minus state, 0 minus 1, something interesting happens. So you put it as 0 minus 1, and then you are going to XOR, or to sum, you can just think of this as sum mod 2, the value of f of x to 0 and of f of x to 1. But if f of x is 0, this gives you back minus, because 0 plus 0 is 0, 1 plus 0 is 1. But if f of x is 1, this one becomes 1, because 0 plus 1 is 1, and 1 plus 1 mod 2 is 0. So if f of x is 1, you swap them to the two of these. And this introduces a relative phase that depends on the input x. So by putting x in superposition, you actually have this relative phase that for some x, this is minus 1, and for some x, this is 1. And this y is just separable. You can just, usually you don't even write it because it's not doing anything there. So the goal of this section is that we are now going to exploit this interference pattern in this phase to recover secrets that depend on x. And for that, I will go to something that would have been presented to you first in some class on quantum computing, which is Simon's algorithm. And Simon's problem asks you to given a function that maps, that takes bit strings and maps to some, well, actually, this is wrong. It should be to maps to some bit. The goal is to find some, and you are promised, yeah, that's it. You are promised that there are two inputs, X and X or S, that give you the same output. Of course, if S is 0, then this function is injective. And your goal is to find this shift S. So how do you do this classically? Well, this very complicated thing that I wrote here, it translates to essentially you try all X, and if you ever found some Y that has the same X, if you already seen some pair Xj, Yj, for which the same Y that you verify in the current X, then the output of Xi times Xj is exactly S. Otherwise, you keep iterating. If you finish and you have not found any, then it means that the function was injective and S is 0. So classically, this requires you to do the enquiries. You have to go over the full domain. But in a quantum computer, you can actually do it with a linear number of queries. How do you do that? So I'll go through this. So you start with two register in the 0. Well, you just get two registers, and you prepare them. The first one in the uniform superposition, second one in the 0 state. Then you are going to call your oracle, and your oracle will prepare f of x in the second register, just like Shor would prepare a to the x mod n here. So you're going to measure the second register, and you get what? You get some y0 that is the image of x0, but we know that there are two images that give you the same y0, is x0 and x0 plus s. Again, I mean, this should be very familiar to you, because in Shor, you would have like all the a to the r, a to the r, a to the r, a to the 2r, a to the 3r, a to the 4r, which is a period. So the period here is s, and this repeats s times. This repeats just once. So what you do, so now you are going to do something a bit different. Instead of doing quantum Fourier transform, you actually will do something that's called the Hadamard transform, which is very similar, but instead of doing this kind of thing of putting your function on this exponential that is divided by 2 to the t, you just put the exponent, the 2 to the, it's just t is equal to 1, let's say. And if t is equal to 1, if t is equal to 1, is the same as going e to the pi I, but e to the pi I is just going 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1, right? It's clear for everyone? So in a sense, what you'll get by doing this is that you get some function that is going to be 1 when x, when the internal product of x and y for each y is 0, because this will cancel and this will sum over the domain of y. And it will actually be, this probability will be 0 for any other value of y. So essentially, you will always measure some y that is orthogonal to x. And it's orthogonal, of course, because s times y is 0. This is what you'll measure. And if you, so you repeat this many times, and after a while, you will get enough linear independent vectors that give you, that allow you to solve the system and recover y. And this is good because now there are some ciphers that have exactly this structure. For instance, this is a simple cipher. It's called the Evan-Mansour cipher. This is the second example to be proposed. The first one was this one. And here you actually have two keys, one that is XORed before, and the other is XORed after some public function f. And this is the equation of the encryption. And if you see, if you like squint your eyes a little bit, if you put here m plus k1, it will actually just can't, so sorry, I'm going to define this function, not this one, which is going to be this XORed with P of M. M, I can choose whatever I want. And this P of M, I can compute because P is public. And I compute this function F of M. But if you compute this function, I expanded here by just putting this here. I just expanded this term to this term. And if you look at this and you put M, instead you put M plus K1, K1 cancels, and here appears M plus K1. So this function evaluates the same value, whether you evaluate it on M or if you evaluate it on M plus K1. So this means that Shor's algorithm allows you to recover K1 immediately, because this function is exactly the same statement, the same promise of Simon's algorithm, of Simon's problem. And it turns out that K2 you can just recover more or less easily just from K1 and public information. Anyone has a question? Maybe I went a bit too far, but I think it's okay. Also, we are almost out of time. So. Good. I'll skip this one, but there are many more applications of this kind of structure. And just to have some brief discussion on like more conceptual results of why all of this is important. So we've seen that quantum algorithms actually apply directly to cryptanalysis, and we've seen these applications both in the Q1 model, where we allow the adversary to run an algorithm in a quantum computer offline, and also in the Q2 model. And yeah, so one thing that, I mean, for you probably is interesting, or I mean, for me is interesting, but it could be something that you would be able to explain to me, is that how these primitives be implemented in quantum networks, because that would be critical to understand what is the Q2 model that we have to look at. So, of course, an important study is like whether these post-quantum assumptions, they are actually quantum secure. Are they secure in the Q1 model? Are they secure in the Q2 model? So this is something that I believe is not well studied. Right. And of course, we didn't cover much, but of course, this fact that we keep modeling these primitives as black boxes, as oracles, is something that we also need to understand. What does it mean, right? This is like, it's a black box, but in practice, we actually need to implement something. So probably we need to come up with good and bad ways of implementing. So maybe we need to, every time that we receive a message, we need to implement a measurement to enforce that the states are classical. Does that have problems? There are some results that show that maybe you still have problems by doing that. So this kind of practical details, they are very important. And I guess this is something that is not yet truly studied, and that I would like to encourage you to think about these problems a bit, and if you want to discuss with me as well. Yeah.
Why don't I not grab?
Yeah, sorry, I didn't explain what was this. So maybe if you don't know what this is, just ignore. This is just an example of a model that you typically implement in a quantum computer, and you model it through this it's called a random oracle model and quantum random oracle model. Yeah, sorry, this is clearly not a bad pedagogical practice. It should not be there because I didn't talk about it. But yeah, it's just an example of what I mean with this question of like, there are so many structures that we implement, and that when we make a proof, we say, but this is just oracle, we call this oracle. But I mean, in practice, it will have to be implemented in some way, and it will be implemented with some algorithm. So what does it mean when this algorithm is run inside a quantum computer, for instance? So these kind of questions, I think they are important. And one very active research topic in post-quantum security, in particular in the Q2 security model, is proofs in the quantum random oracle model. Anyone has more questions? Yeah.
Another question to the previous slides.
Yes.
Because you said that graph isomorphism is hard, probably because the group is not clear.
Yeah.
I can't follow what group you're talking about.
Okay, I mean, we can discuss what are the algebraic structures behind this. I mean, I on purpose did not go into much detail. So my goal was mostly that my goal was mostly that. So there's this big family of problems for which Shor is just an instance, right? And these are many problems that fit in this. I mean, I didn't explain any algebraic structure behind any of this. But if you are interested, we can definitely talk about these more strange problems. I'll be happy to. Yeah.
Like this big family of problems, is this something that people realize that there was this big thing and it stays like that, or is this realization gives you somehow a way that even simple problem, we know that there is a straightforward way to do some sort of quantum algorithm?
Yeah, we have a straightforward way to have a quantum algorithm. So you could just describe Shor's algorithm as a generic implementation of this. So of course, the algorithms might not be efficient especially for these two problems. But the way they come up with this general problem is that, I mean, the structures are pretty obvious. And also these problems are like very, very famous problems in computer science. They are not invented to fit this setting. They are really, like graph isomorphism is the basis of lots of algorithms in general. A billion, so you have a group, by a billion I just mean that the group law is a billion. Yeah, that's what I mean by a billion. I mean, we could discuss later. The composition, I don't think is a billion. Yeah. Good. Is it?
No questions? No questions, speak again.